All right. So I'll apologize in advance. I'm feeling a little bit under the weather, so if I don't have my normal exuberance for talking about something I'm actually very passionate about, I do apologize. So today we're going to have, just for the sake of time, a very compressed overview of the stuff that I am a developer of, pbdR. We normally do full 3.5, 4-hour tutorials on this kind of thing. So condensing things down to 50 minutes is a bit of a challenge. But we'll talk about the project itself, some quick look at NPI, the distributed matrix stuff that we do, specifically matrix exponentiation, and then we can talk about maybe revisiting this in the afternoon depending on interest. So the project itself is part of this ecosystem of parallel packages available to R. So we are firmly in the distributed computing category. Now, it is true that anything over here works in shared memory. It may not be the most efficient thing in shared memory, but anything over here will work here. The reverse is not true. Okay? If you live over here, you may not be able to get over here unless you were over here in the first place. So our project is all about distributed computing, being able to leverage large clusters, servers, supercomputers. It's a series of free packages. They're licensed under the MPL, BSD, and GPL licenses for a variety of reasons. We like to bridge high-performance compiled code with the high-productivity syntax of R. And we have many methods that actually have syntax identical to serial R, but with a new compute engine underneath to be able to do things distributed. We offer scalable big data analytics, implicit and explicit parallelism, as we will see. This is the ecosystem of packages, and it's only going to get more confusing in a few weeks when we have some new stuff released. So pbdMPI is the base. This is sort of like the RMPI replacement, if you like. There are some differences. We'll discuss them. pbdProf, this is the MPI profiler. It will work with RMPI, but it's integrated very tightly with pbdMPI. pbdNCDF4 can do parallel netCDF4 reading and writing. So these packages are, you should really just think of them as being split for my convenience, but if you just think of pbdDMAT and then these are things that come along for the ride, this is the distributed dense matrix stuff at the moment. Soon we hope to have some distributed sparse matrix stuff. For the moment, everything is dense. And then pbdDemo, which is a collection of, I think, 35 some odd demos of using all of this stuff to solve toy and real problems. The demo includes a 140-page textbook-style vignette that we've written. So we're pretty serious about this stuff. Here you can see some of the foreign libraries that we interface to. So R itself uses LAPACK and BLAS. We talked a little bit about those yesterday. There's an extension to these, which is sort of the parallel version, which enables us to do large-scale linear algebra, ScalePack, pBLAS, and then the communications library BLAX. These sit atop MPI. Our use of them for the R user is almost completely implicit. They're not so fun to actually directly interface, but the hard details are sort of taken care of. We try to hide the distributed data details from the user as much as possible, although understanding the data distribution can improve performance. MPIP is a profiling library, and then these are I/O libraries, and so here we are on top. This is the least squares benchmark from yesterday we discussed. What I didn't show you yesterday was the syntax that I used to generate this benchmark. There it is. I mean, it looks just like R code because it is just R code. Underneath, it's doing something a little bit different. But in R, you have an lm.fit. This is assuming you don't need certain portions of the lm function, which we don't have at the moment. Then lmfit is a much faster way to fit linear models in serial R. Well, the exact same syntax will work for us in pbdR. The only difference is X and Y are no longer ordinary matrices. They're distributed matrices. So we have a lot of very high-level object-oriented programming on top to give identical syntax when we can. And we saw this yesterday. This is still true. that we have this pbdprof package, which allows you to profile your MPI usage within a package or an R script. Okay, so pbdR scripts, they're just R scripts. Okay, we didn't build a different version of R. We built extensions to R that you utilize. So R comes along for the ride. And for that matter, a lot of the choices that R makes, for better or for worse, we follow as well. So we really are trying to make sort of an extension of the R grammar to actually run on, for example, supercomputing resources. At the moment, we cannot run interactively. You can with one rank, but all the interesting things happen. If something's going to break, it's not going to break with one rank. And so there's almost no point. For this workshop in particular, developed a little thing that I call pbd inline. It's available on GitHub, but it's also installed on the cloud image, both the one that you logged into yesterday, which should still be up, as well as the one that you set up yourself. It should be there. This offers pretend interactivity, and I'll show you what I mean by that. It's really just a way to be able to use it without having to deal with SSH and running things in batch explicitly. So instead, you run it implicitly. So let's do a quick introduction to MPI, and it's going to be real quick. MPI, this is the standard for managing communications on these large machines. And it is a standard as opposed to an implementation. There are various implementations: OpenMPI, MPitch2, InvaPitch. Intel has one based on InvaPitch. Cray MPT, there are others. But it's a way of managing, as I said, the memory on nodes that you can't directly manage the memory of. So you manage them indirectly. It enables parallelism via communication on distributed machines. So you tell the other node what you want it to be doing to make it do something, since you can't just directly write to its memory. There's a communicator, which manages the communications between processes. What does that mean? So here's the picture. Okay. We imagine this is one shared memory node connected to another shared memory node, forming one distributed memory computer. Okay. Your communicator is just going to number those CPUs. Or really not even CPUs, you just form what we call ranks. So rank 0, 1, 2, 3, 4, 5, 6, 7. And they're really just processes. Ideally, these would be mapped to the processors, the cores, in some kind of sensible way. Here's one way you might do it. You might say, for each of my cores, I will form one MPI rank. They get numbered 0 through the total number that there are minus 1. Another way you might do things is you might say, well, I'll have 2 ranks, 1 per node. And then within a node, I'll reserve these other cores for things like threading or forking, shared memory computation. This is very typical, and then so is this. But the idea is, a rank is just imagine it as being an R process that has spawned and is in this group. It has a number assigned to it. And so if 3 needs 0 to do something, we can pass a message. And MPI implementations are fairly clever. So if you're on the same node, that message passing is fairly quick. If you're across nodes, well, then you have to go through the network. And so if one wants 5 to do something, then you have to pass messages around through the network, which has latency, built into the network. Okay, so managing a communicator with pbd-MPI, how would you do this? So you call init, open close paren, to initialize. This is fairly similar to our MPI syntax, but there are some simplifications. You call finalize to shut everything down. This is like mpi.exit in RMPI. Rank query, so if you want to know among all processors, who am I? You say com.rank, and that tells you, I am rank 2 or rank 0 or whatever. Com.size tells you the total number that there are. Remember, com.rank is 0 indexed. So the first one starts at 0. The last one will be com.size minus 1. This is just a convention from C programming, the people who develop and implement MPI. We also have some printing utilities. So we have com.print and com.cat. These are the parallel versions of print and cat, but they have some niceties built in so that if you just call print and you have 10 ranks, then all 10 ranks are going to start trying to hammer standard output. And so you can basically just get a soup of mess as they fight over who gets to send the output to the terminal. So these, by default, have some order imposed. As such, they are dangerous. You should never apply these onto yet-to-be-computed things. And I can show you an example of that. Because deep within these things, there's something like if com.rank equals 0, do something. And then at the next step, if com.rank equals 1, do something all the way up to com.size minus 1. If something hasn't been computed yet and there's a dependency, then the ones who are not inside of that first call will be skipped, and rank 0 will basically just sit around waiting for the others to check in. They never will. The thing will just hang. And I'll show you an example of that. But these are dangerous, even though they're very convenient. The way to avoid the danger is just always use them on things that have already been computed and stored, as opposed to just like, print SVDX. That's dangerous. Storing SVD of X and then printing it, that's fine. So here's an example. These are R packages. So we load them, library pbdMPI, quietly equal true, just to suppress. You don't want, if you're loading 10,000 of these things, you don't want, if one of them has a message, then all 10,000 messages would print. In it, to initialize, I might store my rank as com.rank. You can com.print my rank, and then I say all.rank equals true. What that will do is it will orderly print from rank 0. It will print my rank, happens to be 0. It will then go to the next one for rank 1. It will print that value. The value is 1. And here's how you might execute something like this. It has to be done in batch, as I say. Usually you use MPI run. Certain systems have a different dispatch for using MPI, maybe app run or something else. But if you're setting something up yourself, it's almost certainly MPI run. Dash NP is number of processes, the number of MPI ranks. We're using 2, our script, and then the script. Okay, and so I can show you what I mean by the pretend interactivity. So we can do this in pbd inline. So if we hop over to here, so if I do this, oops. Okay, so let's go ahead and source that. I won't do anything yet. The way that I would execute this script, now notice I don't have the loading, the init, or the finalize. By default, the thing that I'm going to use to do that will just do that for you. It's pbdR script, okay? And we can see here that it takes body. So I'm basically mimicking the inline package, which we'll actually see tomorrow. So there's a body here. So this is the body of the script that we want to run, the number of cores. Auto, that will insert loading of pbdMPI and initialize. Auto.dmat does the same thing, but for the dmat package. And then, don't worry about that for a second. So if I do body equals body, cores equal 2, okay, this is what it returns. Can everybody see that? Okay. So here it prints the PID. Why we're doing that, I'll explain in a moment. It just does. But then it actually runs that script. So this is pretend interactivity. These values, this data is gone from this R session. It never was in it. So we don't actually have interactivity. This is pretend. Eventually, we do intend to develop a client server, but this is hard, and you need something scalable. You can't just sort of do the first thing you think of. There's a question?
Oh, wait a minute.
Oh.
Does that mean that the environment, because this is sort of pretending interactivity, that the environment would not be set here? If I call it a variable, which has been defined above library, it wouldn't exist?
Correct. Within the call of pbdR script, it's a new R session. This is pretend interactivity.
Right.
So what it's doing is, underneath, it's calling system, MPI run-np whatever, R script, some temp file where I've dumped body. Make sense? So this is just a convenience basically for this kind of scenario. I wouldn't use this in real life. This is just so we can get our hands on it, because maybe you use Windows where installing this stuff is maybe a little harder. So we can just run everything on the Amazon instance and actually see how it works, interact with it. But this is not the kind of thing that I would want to actually do for a real production run. So why do I print the PID? Remember all this threatening language I used about how dangerous com.print is. So I'll show you if I, for example, we haven't talked about all reduce yet, but this is a function which requires communication. I'll just say that as a given. We'll talk about it, but if I, well, let me show you one thing first. I'll show you this first. Can't make up my mind. So if I execute com.print all reduce on the thing yet to be evaluated, and I call pbdR script core is equal to, I'm going to source that. Now notice, rank 0 is trying to print something, but it doesn't know what to print because all reduce requires communication among all the ranks. In this case, there are 2 ranks. So the 2 ranks, or rank 1, just skipped over. Said, it's not my turn. I'm going to iterate through in this com.print thing until it's my turn. Rank 0, it's his turn first, or her turn first. And so rank 0 calls all reduce. All reduce requires that rank 1 check in. It's not going to check in. So it's actually just stuck forever now. If you're using a normal terminal, and so underneath I'm actually in the system call I'm forking. If I didn't fork and you were in just a terminal, you could control C and that would just kill everything fine. RStudio is a little bit annoying, so I actually have a kill wrapper so I can get rid of that PID. And so it says MPI run killing job. I didn't call finalize. This is bad. It's fine. It did exactly what we wanted it to. We made a mistake in the programming, and so we needed to be able to kill it. We did. So that's why it's printing the PID, is in case something gets stuck. Because you don't want to have all these instances running up where maybe you're not comfortable using SSH and top and kill. So this is just convenience, like workshop kind of stuff. Instead, what you should do, whoops. If I do this, everything should be fine. And it returns something. Maybe we don't appreciate what that is just yet, but it's fine. It works. So as I say, com.print is safe on something that has already been evaluated. And you can call com.print all.rank equal true. And that will do something slightly different. It will print among all the ranks. Okay. But as I say, com.print is not really safe if you're not careful. Okay, so more printing. So if I just say com.print, as we've already seen, what that will do is give you these first 2 lines. By default, it'll tell you who's doing the printing, in this case rank 0, and then it'll do the printing. By default, only rank 0 will print. If we want more, we could specify an individual rank. We could ask for all ranks. And I can say that the printing should be done quietly, in which case telling me which rank is doing the printing is suppressed. Just a utility function. Very convenient. And this is how you would run it. Maybe we'll skip that. The key MPI operations. Okay, so there are more, but these are, I think, sort of the most important ones that you really, before you can really do almost anything in MPI, you have to know how to do these things. You have to know how to reduce, gather, broadcast, and barrier. So reductions. What's a reduction? I think of reduction almost like voting. So we saw an all reduce. What did that do? I said all reduce 1. There were 2 ranks. It returned 2. What did it do? All just means everybody gets the result. Reduce means we add up everything. Each one had 1. 1 plus 1 is 2. Okay. So in this case, you can kind of get a sense for how this works. We can see an example. Gather is a many to 1. It's exactly what it sounds like. You have a bunch of stuff out here. It belongs over here. That's a gather. And all gather would mean that everybody gets the result. Okay. Broadcast or bcast, so this is the opposite. This is a one-to-many. Barrier is a synchronization. So if things are sort of not expected to finish computing at the same time, you can set up barriers so that every rank has to wait until all ranks are ready to proceed. Barriers are often computationally expensive. You want to avoid them if you can, because if it's possible in your algorithm for certain things to race ahead of each other, that's actually a good thing most of the time. It can cause actual issues, and therefore the barrier exists and is important, but it will have a performance cost. Although getting the right thing is perhaps better than getting the wrong thing fast. So in pbdMPI, how would you do these things? So for a reduction, here I'm just explicitly saying what I've already described. Each processor, for example, has some number x. Add all of these things up, find the smallest or largest. These are different kinds of reductions you could do. So you could reduce x, operation equals sum. That will take, so assume every rank has something called x, and it has a number stored for x, like 1 or whatever, or com.rank, just whatever. Reduce will add all those things up, and it will be stored on, by default, rank 0. You can choose which one you want it stored on. All reduce, this means everybody gets the result. Op could also, as I say, be min, max, several other things. Gather, you imagine each process has a number, and when I say a number, this could be, you know, a much more richly structured object. This is just an example. Create a new object on some processor containing all of those numbers. So gather is gather to 1, by default rank 0. All gather to all. Broadcast is just bcast, and it just sort of is what it is. Barrier, just barrier open, close paren, and it just sort of is what it is. Yeah.
So it says a number x, but can x be pretty much any object, or what's the?
Yeah. So there are some interesting caveats there. You can for a reduction. There are some limitations. I think a reduction is inherently numeric. But for like a gather and a broadcast, you could pass around chars. That's much more expensive, but it can be done.
But like in this case, x could be an integer vector.
Sure, of course.
Could be a product.
Of course, yeah. So for example, if you have a vector of integers and you're doing, for example, a reduce, right? What will it do? It will just add up, you know, all the one slot elements, all the two slot elements, and so on.
Same way that x plus x and r.
Exactly right. Okay. Reduce and gather example. As always, we load pbdMPI, initialize with init. Here we see com.set.seed. What's going on here? This is a high-level utility function for managing seeds. Diff is for different, so I want the random number streams to be different when I call this way. When I do so, it's basically just a high-level interface for R-Lecoyer, which is the standard for managing these kinds of things. If you said diff equals false, then every rank would have the exact same seed on them. Maybe that's beneficial for some applications. Maybe, I think more generally, it's more useful to have different random number streams. So for example, we could sample one element from 1 to 10 on each rank. We can gather that, and by default, the gathered object will be stored in a list. We can print it. Now notice I'm com.printing it, but this is safe because I've already done the gather. Unlist is not collective. Unlist is done locally. Then here I could all reduce the number that we sampled. These are just silly toy examples to understand how these operations work. Com.print on it. Again, that's safe. It's already been stored. Print among all ranks. Finalize. So what will this return? One example, well, since the seed is fixed, it will always be the same, I suppose. But what we'll do here, when we gather, we'll get this vector 2, 8. So rank 0 sampled 2, rank 1 sampled 8, and that's the return. And 8 plus 2 is 10, which is what all reduce is returning. Okay. I know this is a little bit quick. We can return to this in the afternoon, but this certainly gives the flavor of the kinds of operations you do. And then you could take this and hopefully easily copy paste. Here the line numbers sort of get in the way, at least in my PDF viewer. Here you can easily copy paste, hopefully. So bcast, this is really more of the same. So here I'm being a little bit more explicit in, for example, construction. What am I doing? So I'm saying if the rank is 0, so processor 0 will store the matrix consisting of 2 rows, 2 columns, elements 1 through 4. Otherwise, I'm just going to store a placeholder for x, because when I call bcast x, every process calls that, and so x had better be a thing on that process, even if it's here in this case just a placeholder. So when I call bcast, the source is 0, because 0 actually has the thing. Store that in y. Bcast is a one-to-many. So now I will print on rank 1 the result for y, and we get what was stored originally on rank 0. Okay, make sense what we're doing? Sure.
I have a couple questions.
Yeah.
I'm missing some of this. I'm not sure if everyone else got this. But okay, so sometimes when you, let's say, in compared to for each or snow or any of the more traditional things that we've shown in the last couple of days, you might have a master node and two slaves. And so you might be distributing processes to the slaves and reducing back onto the master node. So the first question is that that kind of paradigm has totally been abolished here?
Correct.
So
It's a very good point.
You're asking for two. So let's say you were going to some Slurm script. You were asking the cluster for 2 nodes, or 2 processors or 2 nodes is still unclear to me, but 2 things.
Sure.
And you've asked for 2 of them, and you're going to distribute this script to both of them, where one's going to be called rank 0, one's going to be called rank 1. And then, well, where is the compiling happening? How can, if there are 2 things operating, there's not a third thing that's going to take the output of those first 2?
So we don't need to compile anything because we've already compiled the packages, right? And so we're dynamically linking with some MPI implementation. But you bring up a very interesting point that I've sort of underplayed here. There's no manager, there's no master, however you want to think about that kind of thing. This is called single program multiple data paradigm, not to be confused with single instruction multiple data, which is some hardware thing we don't want to get into. This is SPMD. So in SPMD style programming, there's no manager. Everything is sort of operating independently. Checkpointing is needed. But suppose you had two nodes, 2 distributed shared memory nodes, and you want a rank on one and a rank on another. So as long as those nodes have access to some kind of shared file system, NFS or Lustre or something, and that they can actually load up those packages plus R plus the MPI library, then they can access the packages and execute the code. Does that make sense?
Yeah, I think maybe this is a former for this afternoon. Again, I really don't know where everyone else is.
When you said compile, though, you weren't talking about compiling code. You were talking
about the results.
Gathering results.
Sorry.
Okay.
If you think of it, I try to think of these things as an analogy.
Uh-huh.
So if you had a for loop, so the first thing to do when you're writing code would be to write something in a for loop, right? In the simplest way, it's not distributed, it's not parallel, right? The next thing would be to write a for each loop, which is distribute those processes to different cores and then come back to the result. This is a completely batch system that's probably better than either of those options. But I'm just wondering how the thing comes back together. And
Okay. So when you say together, you're sort of implicitly assuming that you had a single instance that fired off these other instances. At the moment, we don't have that kind of paradigm. And we can understand that better with maybe a more hands-on approach, and maybe we can revisit that. But that paradigm is not what we are using here. So we don't have one rank that, for example, mpi.spawn.r slaves spawns a bunch of workers and then collapses the result back. The result may end up just being distributed among all of the ranks. It may not be collected, or you could choose to collect it to a rank. It sounds strange maybe, but it's very freeing. But sure.
I mean, maybe just explain it, but I think like they kind of answer your question. I think you just have to be more explicit. Like if you want like slaves and a master, you just say the rank is 0.
Yes.
You just wait till they're all done, and then they do all the work, and you just sit there.
You can emulate this kind of behavior that way.
Yeah, you just have to tell exactly what to do.
Mm-hmm. And so here is the PBD inline way of doing things. We have other helper tools, for example, task subsetting, get.jid. We've seen something like this. We have things that sort of emulate a manager-worker style paradigm. PBD apply, pbdL apply. These are like the par L apply, and so on. And they're the parallel analogs of apply, L apply, S apply, and so on. The PBD apply is you sort of need the right kind of problem. These basically behave the way you would think, I'll say. So we can emulate this kind of task parallelism, manager-worker style, but a lot of what we do will not fit that paradigm. In particular, the distributed matrix stuff. So a lot of problems in data science really boil down to matrix algebra. And so if you can distribute your matrices, you can handle bigger data. Unfortunately, the distribution scheme that we have is really complicated. It's really complicated for a reason. We're not just trying to show how smart we all are or something. There's a really good reason for this data distribution. The cop-out answer is this is what the Scala-Pack library requires, and therefore we require it as well. The less punty, kind of answer is that it's actually an interesting distribution scheme for load balancing matrix computations. It will not locally load balance to where everybody owns the same number of rows and columns necessarily, but it will load balance the matrix multiply, which turns out to be the most important thing in the world. So what you do is you have a two-dimensional grid. This is all very fast. We just went from ranks, which is 0, 1, 2, 3, 4, 5, to now it's two-dimensional. So it's even weirder. And we're not just two-dimensional on the grid of processors, but we're taking blocks of things and we're cycling through in this strange scheme that may not be obvious at a quick glance. But the local view looks something like this. So locally, so if these are the local R pieces of some global, theoretically global, may not ever actually exist matrix, you have x11, x22, and then row-wise, this is not how matrices are stored in R, as you probably know. x11, x22, the row-wise next element would be x17. So we've hopped quite a bit. We skipped over all this and hopped over here. And then the same way column-wise. So it's complicated, but we manage all of this underneath for you. So you don't have to really think too hard about this distribution. You need to be aware that it exists, because there are some parameters you would have choice over to control. For example, maybe you don't want this to be 2 by 2. Maybe you want it to be, probably, in fact, you would want it to be something like 16 by 16, because that size controls an effect on cache, which is really important for performance. Once you have your data in that kind of format, and we're glossing over things very quickly for the sake of compressed time, we have things like brackets, so you can actually subset on this monstrosity. So if you want to kick out row 0 or column 1 or something, that is possible. It's currently pretty expensive to do so, but you can. R-bind, C-bind, these exist. Again, it's fairly expensive, but you can do it. We have lmfit, which our lmfit is actually really good. We have prcomp. I could spend a lot of time talking about that. We have a covariance, which is pretty darn good. We have matrix multiply. You can solve systems of equations, compute SVDs, take norms, condition numbers, all the great linear algebra stuff. We also have medians, which is sort of difficult, an annoying problem. Means, which is easy, row sums. And the serial code, if you say covx, then the parallel code is covx, only x is no longer a matrix. It's a distributed matrix. So the hard part is getting it into this fiddly little format, but we have some convenience routines to help with that kind of thing. And again, just to show you examples, this code could run on R with 1 core, and it could run on pbdR with 50,000 cores. The only difference is what is stored for the name of the object X, a matrix or a distributed matrix. And yes, we even have apply, regular old apply, although apply is very expensive, so be careful with it. Yes? Why would we split the matrix? That's a great question. Why would we split the matrix? Because here we're looking at a very small thing, right? But suppose you had a 100,000 by 100,000 matrix. That's 75 gigabytes of data. R requires between 2 and 6 copies for almost any operation you do. So now you're pushing over 150 gigabytes of RAM on a single node. Those machines are rare. So to be able to perform those kinds of analyses for a really big single problem, a really big single big data problem, you have to chop the data up and send some of it to this node and some of it to that node. So matrix exponentiation.
Before you do that,
Sure.
how would you get the data into that DD matrix?
There are lots of ways. We have some simple ways. So assuming that your data is like big but not astronomical, what you might do is read in on one rank. And then we have casters. In R, you cast with as dot matrix, as dot vector. Well, there's an as dot DD matrix. DD for distributed dense. A DS is coming soon. So you could say as dot matrix on something that you stored on rank 0. It'll broadcast out the pieces. If your matrix is, for example, fairly simple, like in R, some of the things you would do is like matrix. Well, we can go back. In R, you do things like this, right? If you add DD in front of that, the exact same thing will work, in fact. So if data is global to all ranks, we can chop it up, and in fact requires no communication to do so. So we have some readers for netcdf data, netcdf4 data. But that is really the hard part, is getting it into the right format.
So you have a 75 gigabyte matrix.
Mm-hmm.
What do I do?
Depends on your resources available. You know, if you have something that big, you may not be able to read it all in onto one thing and broadcast it. So maybe you read in chunks of it and broadcast. Maybe you read in, for example, we have routines to be able to do this, but they get complicated and depend on how your data is stored. A lot of people, even for really large stuff, are using CSVs. I don't recommend it. If you're living in that kind of world, you know, you really quickly become I/O bound. So it just sort of depends on where the data is living, what kind of machine you have. But that is sort of the hard problem. Yeah.
So what do you recommend?
So CSV is fine for the things that it's fine for, right? Probably a lot of people here deal with like FASTA files, and at the scale that a FASTA file would store data, that's fine. So beyond that, for really big things, it really just sort of depends on where you're working. XML, there are various XML storages that are sort of generically good for large storage. We tend to default to netcdf because there's a very good parallel reader for it that we happen to have. Unfortunately, the answer depends. As it turns out, things like communication and reading data turn out to be the hardest part of really large-scale computing, the things that almost don't matter in small-scale computing. You could make terrible I/O choices and it's fine. All of a sudden, you make the best possible I/O choices and still your problem is completely I/O bound in large-scale computation. So there's a whole swath of things we're sort of glossing over. Yeah.
So what sort of scale of data are we talking about where this becomes an issue?
Where I/O becomes an issue?
Yeah.
Definitely by the hundreds of gigabytes, depending on how much reading and writing you're doing, tens of gigabytes. Okay, so matrix exponentiation. So from calculus, we all remember that we define this exponential function in this way. We can do the exact same thing for a square matrix, where we'll just call that expom of x. It's some n by n matrix. And here I'm just scaling all the elements when I have this scalar here. And then in the 0 case, we'll take it to be the n by n identity, just so things sort of match up. Unfortunately, this is probably the worst possible way that you could try to compute the thing, even though this is the way we define it. If you're over here, it's not an unreasonable approach to, you have some kind of relative error that you're interested in, something being no larger than the previous iteration, and you just sort of keep going until that relative error is small. If you try something like that here, you'll get really bad estimations. It's called numerically unstable implementation. So you have to think a little bit harder. This naive implementation, as I say, leads to a huge loss of accuracy for many matrices. And this has been vigorously argued for over 30 years, the best way to compute matrix exponentials. One of the standard papers, there's a 1977 and then a revised, I think, 2003 paper, 19 dubious ways to compute the exponential of a matrix. It's a really great paper, and in the revision, he recommends ExpoKit, which we've heard about, as probably the best and most comprehensive way of actually doing that. And that was completely true until 2009, where Al-Moe and Hayam develop a new scaling and squaring algorithm for the matrix exponential. So for dense matrices, the method of computing the exponential in ExpoKit is a scaling and squaring technique, but it's a little bit overzealous, which leads to, one, a loss of accuracy, and two, unnecessary computation. So this is actually a really, really impressive method for sort of slimming things down a little bit. So we scale and square. What does that mean? We have something j, which the estimation of j is really the magic of this new method. So j is some integer, okay? And finding that takes a little bit of elbow grease, and it depends on like the norm of the matrix, and it's a little cumbersome. But there's something j, and we form 2 to the j. And then we scale x by 2 to the j, called n. We do a Pareto approximation, which is this numerical technique, not worth spending a lot of time on. In ExpoKit, they use an order 6. We'll use an order 6 if that means anything to you. If not, it really is irrelevant. And then we do a matrix power by squaring on the result of this Pareto approximation on n again. So you have all these matrix multiplications going on to square this thing out.
What's J again?
J is a thing that is how to describe it? It is a value that I really don't want to get into because it's a bit cumbersome. It's just some number that. What's that?
But it's fixed. Like we don't have to.
It depends on the matrix. So this J depends on matrix X. And the details are cumbersome. They're very well written in here if matrix algebra is the kind of thing that wakes you up in the morning. But the value J is just a little bit fishy, basically. So in pbdDMAT, we have 2 implementations. We have a serial and a parallel one. And they both have the exact same dispatch. The only difference is, so for example, if you just have some matrix, whatever it is, you could call expom on that ordinary R matrix. It'll work. You could cast it as a DD matrix. This is one way you might do that. Expom dx, it's the exact same thing. The dx carries no semantic meaning. And the exact same, it'll perform the exact same kind of operation, only in parallel now, on a distributed object. So not only is it parallel, you could run it on multiple nodes. And I'm really proud of this, but it's going to take some explanation. So this is a speed-up plot. Remember yesterday I told you that this is the theoretical maximum, and we should be living over here. We're not. So when I first looked at this, my first thought was like, oh no, what have I done wrong? But I actually understand this now, and I'm very proud of it. So first thing, so this is a speed up relative to 1 core. So this is my 1 core implementation. Okay. In just doing some like package cleanup on RexpoKit, I was able to improve the speed by about 30-35% in the exponential in RexpoKit. My serial one has another 15% improvement over that. My parallel one is behaving quite well. Now, why? So when I started talking with Nick about what kinds of problems were really slowing him down, he said about the scale he was working, things took like between 5 and 10 seconds. and he's having to do all these things over and over and over again, and it's just very expensive. So that was the scale that I was working at, and we basically just really lucked out. Why? At that scale, on the computer I was running this on, Darter, a supercomputer at the University of Tennessee, at the scale we were working, as soon as you jump from 1 to 2 cores, you're cutting the data in half, splitting across 2 cores. On that machine, the data suddenly fits in L1 plus L2 cache. And so this cache effect that I've hinted at a few times really becomes pronounced. And as we split the data more and more, not only the data, but the copies of the data fit in L1 plus, because we're multiplying 2 matrices. So the things start fitting more and more in L1 plus L2 cache, and we get this really, really nice effect from the fact that it's this entirely compute-bound problem. We have hundreds of matrix-matrix multiplications going on, and so we can really, really exploit modern processor architecture, basically, to get a very impressive-looking result. Now, to put this in context, if I were to, this is 1 node. If I were to jump to 2 nodes, it would plummet because of the communication over the network. As soon as we get out to 2 nodes, it would also start running out of work very quickly. If we took a really big problem, this is not very big. And by the way, for matrix exponentiation in general, you think multiplying a 2,000 by 2,000 matrix together, this occurs in fractions of a second on your computer. An exponentiation of such a matrix on 1 core takes 20 seconds. So it's a really compute-bound problem. And if we took a really big problem and ran this, you wouldn't see nearly this good a scaling. We just sort of lucked out, and we were able to really tailor something towards the specific problem at hand. But this is a very general implementation. I expect that I can actually speed this up by a factor of 2 for Nick's specific problem. I just haven't had time. But I'm pretty happy with it so far. So a quick wrap up. We have the PBD demo package. It's available on, all of our stuff is available on CRAN. The PBD demo has a 140 some odd page vignette. We call it Speaking Serial R with a Parallel Accent. Has lots and lots of examples and explanations about how to do actual distributed computing with R. We have a full tutorial at UseR 2014. We probably will have a tutorial at Exceed 2014. We may or may not have one at SC 2014. But that we definitely have one at UseR, so that's available. So some quick questions before we wrap up, and maybe revisit this in the afternoon depending on interest. Questions?
Were you doing this just on a PC, right? So you had it on the cores, and you said that it kind of fell apart when you had more than 1 node.
So
Was this wasn't
this was on 1 node of a supercomputer. Yeah. So it's a fairly new one too. So if you tried this on your desktop, you might not dip quite above. You would be hugging that line very close. But basically, the architecture on that computer, we were really able to exploit the cache with this specific problem. Mm-hmm.
So if you're programming something, and chances are most of the time it's going to be in shared memory, but you think to yourself, well, I don't know, people might have bigger data sets than I do, and they
Mm-hmm.
want to use a supercomputer. What sort of performance hit would you take by using pbdR just coded up from the beginning rather than, say, some other,
Sure. Great question. So it depends on which part of pbdR you're using, the performance hits you will see. So there are some things like if, for example, if you're really interested in matrix-matrix multiplications, let's say, what would be better, using our distributed matrix-matrix multiply or using a like OpenBLAS, GoToBLAS, MKL for a shared memory parallel BLAS? It really depends on the problem size. Sort of the smaller you are, the better the shared memory stuff will be. The larger you are, eventually you start running into these physical limitations of a single node. The syntax will be the same except for getting the data into the right format. So the closer you live to linear algebra, the more of PBD DMAT you can very easily swap in and out. The farther you get from that, the more hands-on it is. And if you really are convinced you're mostly living in shared memory, there is a there is a big hit you'll take just from MPI run. That has a cost up front. So if you're doing lots of small, quick computing, I would almost argue R is not a good fit for that in the first place. But MPI run has like an upfront cost. It should diminish over time for a long compute problem. But which one would be better or worse? I would say, this is not great at small things. Small for me is, sub 10 gigabytes is where I get iffy. Over that, we do great. Okay?
Okay, let me take a poll. So, something that you didn't have time here to get into, like...
Almost anything.
Yeah, well, and specifically, like, more higher level things.
Sure.
So if you want to do a matrix multiply, you didn't, like, give an example of doing that, or running a LM fit on a whole bunch of different nodes, or
Sure.
something like that. Is that something people, if you'd like to see that, sort of more higher level programming where you're not actually doing a communication, but you're just using the built-in tools, you could do that in the afternoon.
Yeah.
So if you're interested in seeing sort of more, you don't want to change your programming style, you don't want to learn MPI, you just want to distribute your job to many nodes. Those higher level things, he can do those things in the afternoon and show you how to, you can give him a problem, he can talk to you about how to do the matrix multiply, or solve the normal equations, or whatever, in a distributed environment, right? And even show them a distributed environment.
Sure.